Hello everyone, welcome to Civil Engineering and Stuff. And in today's video lecture, we will be discussing a very important topic in transportation engineering, and that is the side distance. Side distance is a very important parameter in geometric design of the road, especially talking about the horizontal curve. It's a very important topic, and in this video lecture, we will be focusing our discussion over the stopping side distance. All right, and in this lecture, we will be discussing only the theoretical part of the stopping side distance, and the numerical part we will make a separate video and we'll discuss in detail the numericals on this topic, stopping side distance. All right. So without further ado, let's start with the topic, that is side distance. If you want to define the side distance in terms of transportation engineering, side distance is basically the minimum visibility that is required for a driver with a specific height to see a stationary and a moving object from a safer distance. Why do we need to take into account the side distance in the geometric design of the road? You can very well visualize that as and when you are moving along the road, you may see a lot of obstructions that can be in the form of moving objects, that is the moving vehicle, can be in form of stationary obstruction, that is maybe some big boulders might be there, some trees might be there, or it can be many, right? Likewise, as and when the vehicle is moving along the curve, we want the vehicle to have a safe side distance as and when the vehicle is moving along the curve. So taking into these situation into perspective, the side distance that we want to have on the road must fulfill or must include these three situations. The first one is the stopping side distance. That is, if a vehicle sees any obstruction on the road, any form of obstruction on the road, the vehicle should have a sufficient distance to stop and be at a safer distance from that obstruction. So that is what we call as the stopping side distance, and that is what we are going to discuss in detail in this video lecture. Second situation is to overtake the vehicle safely. So if a vehicle is moving behind a slower moving vehicle, then the vehicle can safely overtake the slower moving vehicle without causing any trouble to the vehicles that are moving on the road, right? So that is the another situation that we have to take into consideration. The third is the safe side distance when the vehicle is entering an uncontrolled intersection. Uncontrolled intersection means that, first of all, intersection means when two roads are crossing each other. Uncontrolled means that there is no traffic management strategies per se being installed, right? So in that point of view, the vehicle that is moving through that uncontrolled intersection, it should have a safe visibility. So as and when the vehicles that are crossing the road can safely mitigate and weave through the road section. So this side distance that we are providing on the road must fulfill these three situations, and the overall aim is to satisfy these three conditions. That is, the driver traveling at a design speed has sufficient side distance or length on the road visible to stop vehicles safely in the case of visibility of obstruction. What we have discussed so far. All right, that is a vehicle that is moving on the road. As and when any obstruction is seen by the driver, the vehicle has a sufficient distance on the road to stop. Second is driver that is traveling at design speed, right? All the discussion that we are going to do, we are assuming that the vehicle is moving at a design speed. So when the vehicle is moving at a design speed, the vehicle can safely overtake a slower moving vehicle without causing any trouble to the neighboring vehicles that are moving. And then the vehicle entering the uncontrolled intersection has a sufficient visibility. All right, so that is the overall aim for designing of the side distance on the road. So coming to the main topic of this video lecture, that is the stopping side distance, right? So discussion over the overtaking side distance and the uh, visibility in an uncontrolled intersection, that is a part of the next upcoming video lectures. But this video lecture is totally dedicated toward the stopping side distance. All right. So let's discuss about this stopping side distance. So we have we had a discussion that what is stopping side distance. That is when a vehicle is moving with the design speed v, and this vehicle sees any obstruction. So definitely the driver will observe this obstruction, and then it will react to it, and then it will apply the brake. So the distance covered by the vehicle, the distance that is covered by the vehicle, and comes to the total halt. Okay, the vehicle then comes to the total halt. V will be equal to 0. So this distance that has been covered by the vehicle is what we call as the stopping side distance. This is the distance that is being covered after the driver has reacted to the obstruction. It is what we call as the stopping side distance. Now this stopping side distance is basically is a summation of two important distance that is covered by the vehicle. The first one is what we call as the lag distance. This is what we call as the lag distance. And the second is what we call as the braking distance. This is what we call as the braking distance. Okay. So your so this total distance required for the vehicle to stop is a summation of lag distance plus braking distance. So let us discuss about what this lag distance is and what this braking distance is. So your lag distance is the distance covered by the vehicle during the reaction time of the driver. Okay, so basically what happens that the driver looks at the obstruction, right? The driver looks at the obstruction, and then the driver reacts to that obstruction. So there is a certain time that is elapsed during all these process, and during that process a certain distance is being covered by the vehicle. So that distance is what we call as the lag distance. All right, so your lag distance is speed into time. So your lag distance will be v, that is the design speed of the vehicle, into tr is the reaction time that has been elapsed during this process. All right, so here in this case, your tr is your reaction time. Tr is the reaction time of the driver, which varies from 0.5 second to 5 seconds. Now this range of 0.5 to 5 second depends upon the type of driver that is driving the vehicle. So the experienced driver, young experienced driver will take lesser time to react to the obstruction, while an older person will take a much more time to react to that situation, right? Because of the less active motor reflexes. Likewise, a new young driver or amateur driver will react differently to that situation, right? So this reaction time is usually taken as 0.5 to 5 seconds, varies from 0.5 to 5 seconds, and generally it is taken as 2.5 to 3 seconds. Okay, so how does this we came to this conclusion that the reaction time is 0.5 to 5 seconds. There's a theory for this. That theory is what we call as the PIV theory, and I have made a separate video in detail about this PIV theory. But since this is very important in terms of stopping side distance, so I'll again discuss about the PIV theory. So basically, PIV theory is talks about the overall reaction time that takes place for a brain to process the things, right? So at first, what happens that we have the driver or uh, any human eye. First of all, it perceives the situation, right? It sees the situation, and then the signals are being actually sent to the human brain, right? These are sent to the human brain, and that is what we call as the perception, right? Time to send sensation from eye to brain, right? So this is what we call as the perception. Now what does the brain do? Brain assesses the situation, right? And that is what we call as the intellection time, right? Time to rearrange different thoughts, right? So we have so as and when the signals are sent, perception is done. Now the brain will process the situation, right? It will rearrange different thoughts, it will assess the situation, and then based upon the efficiency of the driver, it will react, right? It will react. And after this intellection and emotion, this reaction is basically emotion, the time elapsed in the emotional sensation, then the brain will give the order to react to that situation, and that is what we call as the volition, right? Time for the final decision. Okay, so this whole process usually varies from 0.5 to 5 seconds. Okay, and that forms the basis of this reaction time. Okay, and generally at an average it is between 2.5 to 3 seconds. So this is your lag distance. Next comes your braking distance. So once the the driver has reacted to the situation, the driver applies the brakes. So at this point, the driver applies the brake. So after the application of the brake, there might be some skidding or slipping of the vehicle, or minimum distance is being covered by the vehicle. As you may have observed, right? As in when you are moving along the road and you apply brake, no matter how small, if you are moving at a decent speed, smaller distance is being covered by the vehicle, right? And that is the distance that we call as the braking distance, the distance covered by the vehicle after the application of brakes. Okay, so your braking distance is the distance covered by the vehicle after the application of brakes. Now, what is the expression for that? How do we deduce that expression? So let us find out the deduce that expression for the distance covered by the vehicle after the application of brake. So for doing so, we'll assume a few things. The first thing that we are going to assume is that brakes are applied fully, right? And wheels are fully jammed. And after doing so, the vehicle moves just by skidding over the road surface. These are the two assumptions for doing so. Now to find out the braking distance, To find out the braking distance, I'm going to assume a vehicle moving in an inclined plane. So it will cover both the scenarios: the vehicle moving on a straight road and the vehicle moving along the inclined plane. So it will, and I'll discuss if what happens when the vehicle is ascending and what happens when the vehicle is descending the inclined plane. Okay. So in this scenario, we have this vehicle that is moving up the inclined plane. We have the vehicle that is moving up the inclined plane, and the vehicle and the driver has applied brakes. Okay, so this vehicle was moving with a design speed, and the driver has applied brake. So after the application of the brakes, the vehicle comes to an halt. Right. So V is now equal to 0. All right, and this is the distance S. This is the distance that has been covered by the vehicle. Okay, so this distance S is what we call as the braking distance. This is the braking distance. Okay, now how to find out this braking distance? So first of all, we will see what are the components that are supporting this braking distance. Okay, so we know that basically the force, the weight of the vehicle mg will be acting downwards, right? And if we bifurcate the component, we have, this is the angle theta, so this will be theta. So we have this mg cos theta as the normal component, and then we have the mg sin theta, mg sin theta. Okay, and along with that we have the friction force that is going to be working in our favor, right? That is, it will help the vehicle to stop. Okay, now this moving vehicle was having certain kinetic energy, right? So certain work has been done by the brakes to stop the vehicle, right? So first of all, the this moving vehicle, the kinetic energy, that was there in the moving vehicle, right? In the moving vehicle will be what? Half into m into v square. Okay, where m is the mass of the vehicle, and v is the velocity with which it is moving. Now, for a vehicle to stop, a certain work has been done by the brakes. So the work done, so the work done by the brakes will be force into distance. Okay, the work will be force into distance. Now, what are the forces that are acting towards stopping this kinetic energy? We have two forces. The one force is the force of friction, and the second is mg sin theta. Okay, so we have two forces. One is your mg sin theta. One is your mg sin theta, and other one is your friction force that is acting. Okay, into, we have the distance that has been covered. Now, since this is the friction force, so the kinematic force of friction, kinematic force of friction, this kinematic force of friction is equals to the coefficient of friction that we will assume to be F into normal reaction, into normal reaction in this case is mg cos theta, right? And F is your coefficient of friction. Okay, so we have mg sin theta plus F into mg cos theta into S. All right. So this work done should be equal to or greater than the kinetic energy. Then only the vehicle will stop. Right. So we have we have this we have this kinetic energy lost should be equal to the work done. Should be equal to this work done. Right. So we have half mv square is equals to mg sin theta plus F into mg cos theta into S. What we are interested in? We are interested in finding out this S, that is the braking distance that has been covered. So your S will be equals to V square divided by 2g sine theta plus f cos theta, right? I have simply cancelled the m. All right. Now, what I can do here is I can simply take out the cos theta as a common factor, and then I will have tan theta plus f, tan theta plus f. And we know that when theta is a smaller value, cos theta value is almost equals to 1, right? Cos theta value will be equals to 1, and tan theta will be what? Tan theta, and tan theta is nothing but the slope of the road, right? So we have s equals to v square by 2g f plus s. That can be taken in percentage, right? F plus s. Now see what we see here is f plus s, right? F plus s, because here in this case, this slope, since I've taken s as the breaking distance, so I'll just change this into n. Okay, I'll change this to n. So here this slope is basically contributing. It is contributing to the braking, right? So that is why we have taken it as a plus. Now, if it was a descending gradient, if the situation was different, and we had the vehicle that is descending the gradient, then what will happen is this weight will act here. This is a theta, and ng sine theta will be contributing to the velocity. It will not be contributing towards the stopping of the vehicle. So in that case, when the vehicle is ascending, when your vehicle is descending the gradient, so in that case, your s will be v square by 2g f minus n, right? S minus n, right? When it is going downwards, okay? Because here, because the slope, it is contributing towards the motion of the vehicle. It is not contributing towards the braking of the vehicle, right? That is to stop the vehicle. Okay. So this is the expression for your braking distance. Correct. Now coming back to the main topic, that is the side distance. So your side distance, your side distance, your side distance will be equals to, leg distance is 0.278 v into tr plus v square by 2g f plus minus n percentage. Now plus minus depending upon the vehicle is ascending or descending. Now in case we have a flat terrain, then n will be equal to 0. So v square by 2g f. Okay, that will be the expression. Now here v is in kilometer per hour, right? So when I convert this v into meter per second, because here in this expression tr is in seconds, right? So what I will do, converting kilometer into meter, what I will do, multiply by 1000, and hour to minute into second. So this will be meter per second. So the expression comes out to be 0.278, 1000 divided by 3600. So that is why here it is 0.278. Here v was in kilometer per hour. I will again multiply it by 0.278 square. Okay, so I'll just rewrite the formula finally. I'll read the formula. So the formula is, if 0.278 v into tr plus 0.278 v whole square divided by 2g f plus minus n percentage. Okay, when we are writing 0.278 v, this means the value of v we will keep in kilometer per hour. Okay, we will keep this. So if in the question the value is given in kilometer per hour, we'll keep that value only, because what we have done is we have multiplied the factor 0.278, right, and has converted the value to meter per second. Okay, so this is the formula for stopping side distance. Okay, now it becomes very important to discuss few important cases with respect to the stopping side distance. So in case, I'll write case here, and then the total side distance. Okay, so in case we have one lane, one way road, or one way traffic, or or we have we have two lane, two way traffic, or we are taking your headlight side distance. we are taking headlight side distance. In all the cases, the total side distance is nothing but the side distance only that we are finding, right? However, in the case when we have one lane and we have two-way traffic, we have two-way traffic, then in that case, it becomes twice of stopping side distance. Okay, it becomes twice of stopping side distance. All right. So this is the theoretical discussion over the stopping side distance. I hope the lecture is clear to you all. And if you have any doubt in this, you can always ask. And in the next lecture, we will be discussing a numerical on the topic stopping side distance. Thank you for watching. Have a nice day.